Hey everyone, what's going on? Welcome to Focus AI. So today we will be looking at what is curse of dimensionality. Now this is a very vast discussion. That might happen, but I will try to keep it short. This field of the problems in high dimension actually affects in many areas of science. So machine learning is one of those areas. So it's also very vast. So I will try to do, I will try to concentrate on mainly the two problems as a machine learning engineer you might face with high dimensional data. Now, let me be very clear here. What do I mean by dimension? Like you might be wondering, like, what is the dimension coming here? So in machine learning, we use data, and the data consists of input and output. Like if it is a supervised problem, then it will be having the output, else not. So the input is common. And we won't say input in machine learning. What we say? We say feature vectors or feature matrix, which is a which consists of many feature vectors. So the length of the feature vector, a single feature vector, is called the dimension. Okay. So in the iris data set, we have seen that each of the feature vectors are having four individual values or features. So the dimension was four. So in real life, when you will start working in real life project, I will also show you like when you will extract the feature or when we will get the features of real world data set, the dimension sometimes increases drastically, like even hundreds, sometimes thousands, and in rare cases it might go to tens of thousands. Now, working with this high dimensional data might be problematic. So we'll discuss two of the main problems with high dimensional data. So what is curse of dimensionality? So from the definition from the Wikipedia I have taken, like the curse of dimensionality refers to the various phenomena that arise when analyzing and organizing data in high dimensional space that do not occur in low dimensional settings such as the three-dimensional physical space of everyday's experience. So I always say that okay, whatever we will do, we will try to understand in two dimension and then we will map it to higher dimension so that it will be better for us. But the one thing which is actually clearing us from this definition, that sometimes these lower dimensional constraints or intuition might not be the same in higher dimensional spaces. Even sometimes it's not as well as kind of commonsensical also. So like just think like this shaded green region, you can see this shaded green region is actually think like a high dimensional space, say 1,000 or 10,000 dimensional space. Okay, now you are doing a simple classification and you have some data points. Okay, so this is actually the say negative data points and these yellow pluses are positive data points. Okay, now in this high dimensional space you have this much data points. Now the rest of the shaded region is vast. It The data points covers only this much area, only this much area. Okay, now for any machine learning problem, what we have to do after the training on all these data points, say I have to give a new query point. Say this is my new query point. Now we can do various kind of machine learning algorithm to predict in which class it might be falling into. So from k-nearest neighbors, so we can say that okay, this new query point might be into positive classes or negative classes. But think like this, if this is the query point. Now think intuitively, think logically. Like this is actually very far away from the main cluster of data points in this high dimensional space, isn't it? Again, I'm repeating, this query point is much far away than this whole cluster of data points which is present in this high dimensional space, this shaded green region. So now, does this make sense like any algorithm? can do things, because in this shaded region we don't know if this is in the positive class or if this belongs to the negative class, we don't know. So that is one problem. So the thing is that if the dimension is increased, then to get a better performance, the number of data points should also be increased drastically. So say this is the scenario what we were discussing. Now we have some small number of data points, but the dimensions are huge. So the number of data points is not actually covering the whole, it's not actually covering the whole dimension, right? So we are getting low performance. So now we have to get better performance, we have to increase the number of data points, and that is not always available. I mean, data is very costly, you cannot get data as much as possible. This is the first thing. And the second drawback is that even if the data is available, you have to spend money on that, you have to spend time on that, you have to buy resources, you have to wait for days or even weeks for the training. So this is the problem of high dimensional data. There is something called huge phenomena. So it is saying that considering fixed number of data points, if the dimension is increased, the performance will decrease. And that's true, very true. That's what we have discussed now, right? So if we are considering, say I have 1,000 data points, and initially my feature dimension was say 100, and I was getting an accuracy for a classification problem is 90% of accuracy. Now due to some feature engineering stuff, I have increased my feature dimension from 100 to 10,000, but the number of data points were same. Now if I try to calculate the accuracy after the training, I should see that there is a drastic drop. Say from 90% it has come to 80%. So this is the phenomena is covered by huge phenomena, or it is called huge phenomena. Okay, so this is one of the problem we face in high dimensional data. Now the second thing is, the most important thing is that how distance are affected in high dimensions, specifically Euclidean distance. Like if you remember in my KNN tutorial, I said that Euclidean distance is not good for high dimensional data. That time you can use Manhattan distance or city block distance, right? So the reason is that this high dimension data actually affects Euclidean distance. Now let me just go through a mathematical notation here. So the notation is this one. This is very simple. Okay, just don't be surprised like what is written here. It's very simple. So what it is saying, limit capital D tends to infinity, dist max of xi minus dist mean of xi divided by dist mean of xi, such that xi belongs to Rt. So let me break it down for you. So here first let's understand what is this capital D. I think you know it. It's the D dimension we are talking about. It is just the number of dimension. So xi is a vector, okay, and it belongs to a d-dimensional vector of real numbers. Okay. Now what is this dist max and dist mean? Okay. So dist max is the maximum distance between xi and xj, where xj belongs to x1 to xk and xj not equals to xi. Okay. So what is this? Say x is a vector space. Okay. So X is a vector space where we have k vectors. Okay. We have k individual vectors, or you can say like X is a space. Okay. X is a space, and x1, x2 till xk are the number of points in the space. Say a 2D space, and these all the vectors are two-dimensional vectors. Okay. So dist max is that I am considering a point or a vector xi. I will compute each and every distance from xi other than xi. So I'll compute the distance between x1 and xi. I'll compute the distance between x2 and xi, compute the distance between x3 and xi till xi and xk. And then I will find out what is the maximum distance. And that would be my dist max of xi. Okay. Similarly, what is dist mean? The same thing. I will calculate all the distance from xi and I will find out what is the minimum distance. And then I will find out this particular ratio. Let me clear a bit. So once it is done, I found out dist max, I found out dist min. I will compute this particular ratio. Now, in low dimensional or in general theory, what do you think? Like dist max would be much more higher than dist min, right? So specifically this ratio should be greater than 0, right? Just think, like dist max is 5 unit, dist min is 2 unit, okay, right? And dist min is again 2 unit. So 5 minus 2 by 2, it's 3 by 2, which is 1.5. So it will be always 0. I mean, always greater than 0, sorry, right? But it happens only in low dimension. That's why I have given this limiting term. Like if d approaches to infinity, that means very, very, very high dimensional space. Okay. So it would be actually, this value would actually become 0. Okay. This value will actually become 0. And what does that mean? This ratio is becoming 0. What does that mean? That dist max and dist min both are same. And when both are same, that means all the points or all the vectors in high dimensional space are almost equidistant. Okay. So the conclusion is that in high dimension, all the points are almost equidistant. So there is no meaning of applying Euclidean distance, right? We measure distance between 2 points or two vectors because we want to calculate how far they are. I have three vectors in low dimension space. Two vectors are closer to each other and another vector is far from the other two. From that we can deduce that okay, there are some similarity within the vectors, there are some dissimilarity within these vectors, right? But if all the vectors in the high dimensional space are equidistant, so in that time, what is the meaning of calculating the Euclidean distance? There is no meaning, right? All will be in equal distance. We won't get any, we cannot analyze the data itself, right? So this is one of the major problem in machine learning when we approach to high dimension. So now you might ask then, if we want to calculate distance, what do we do? So you can calculate cosine distance or cosine similarity. Now it's not true that in high dimension cosine distance is not affected. It is affected, but not as much as Euclidean distance. Okay. So this thing what I have shown it to you, right? That in case of high dimensional space, all the vectors have almost equal distance they maintain. So I will just show you a simulation or a demo in Python that it's actually true. Okay, so just let me erase it and show it to you. Okay, so this is Google Colab, a collaborative platform for data science machine learning engineer. So it's similar to Jupyter Notebook, but it hosted in specifically is hosted in Google servers, and it's a phenomenal tool. I always use in my personal projects and even my professional projects also. I mean, I always recommend you because it gives you hard drive, it gives you RAM, it gives you GPU. So it's a very good product by Google. So anyway, so let's jump into the code. So I'm importing two things, NumPy and the spatial distance. If you have done my previous class on different types of distances, I have shown you like SciPy is a Python package from where we can calculate any kind of distance by this distance class. So this distance class has different kind of distance methods like Euclidean, cosine, Manhattan, Minkowski, everything. Okay. So, okay, just check here. Here what we are doing, let me run it. Let me see. Okay. So it's not imported. Sorry, let me import it first. Okay, so it's been imported. Okay. So what I am doing, I am creating two vectors with dimension 100,000. So it's a high dimension. So I'm creating two vectors xi and xj with 1000 dimension. And I'm using random because every time I run this, two different vectors will be generated. So this time these two vectors have been generated, right? Okay. Now try to calculate the Euclidean distance. Now you see the distance is 129, right? Okay. Just remember that it was 129. Now again I am running this cell to create another two high dimensional vectors, right? So it has been created again. Now again I'm running this Euclidean distance. See, it's 129. Again 129. Okay. Run again to create two more thousand, 100,000 dimensional vectors. So it's created. Now try to run again. Again it's 129. Like after decimal you can see somewhat variation, but the majority, the distance is equal, right? Like it's not logical, right? I know, but it's actually happening. Like there is a mathematical proof behind that limits I have shown you. If you want, you can check in Wikipedia also. I think there was the proof, but like it's phenomenal, right? Now let me reduce the dimension to 10, from 100,000 to 10, and create two 10 dimensional vectors. Created. Now find out the Euclidean distance. So here it is 1.18, right? Again create two random 10 dimensional vectors. Created. Now check the Euclidean distance. It's 1.27. Okay. Created another two. Now check the distance is 1.28. Now here you can see the variation. I mean, you can see they are not actually equidistant. Now the value is very small, like 1.2. Like I mean, even after a decimal place, if there is a change, that's a change. But in the previous 100,000 dimension, what we have seen, like it was 129 point something. It was all around for 3 or 4 iterations, right? So I will provide you the link of this Jupyter notebook in Google Colab. You can try yourself and check, like, I mean, up to what dimension the lengths, I mean, the distance are changing, and up to what dimension it was not changing, something like that, and play around with it. So what we have learned in course of dimensionality, there are mainly two kind of problems. The first problem is that the vector space is empty and it's vast based on the number of data points. So considering if the number of data points is constant, if we increase the feature vector dimension, the performance will decrease. Similarly, for the distance, if we increase the dimension, there is no meaning of calculating Euclidean distance, because in high dimension, all the vectors are equidistant, almost equidistant to be specific. Okay, so we would be using either having not having distance, sorry, Manhattan distance, or cosine distance, or cosine similarity. Okay, so this is the ending of this video, and I will, yeah, provide the in the description, like what is the link of this notebook and also the slide. So have a nice day. Thanks a lot. Happy machine learning.